Hi guys, I'm having a little bit of a slow math day, so I thought that I would talk about something that was easy for me and is kind of a fun thing to do, just to get going. So so I want to tell you guys about the cube root of true. Cube root of true. So this is kind of a weird thing to say. And I want to explain how the concept of the cube root of true makes sense. And the way to make sense of this is through this a process called arithmetization. So I want to explain arithmetization. This is the first thing. Arithmetization of logic. And this is a common trick. So what you can do is on one side you could have propositional logic. So on one side you have propositional logic. And on the other side, we're going to look at polynomials over the field with two elements. So this is the same thing as Z mod 2. This is this field where 1 plus 1 is equal to 0. Okay, so there's only two elements in here, and you can make a field out of this. Well, let me just start with the conversion. So true goes to 1, false goes to 0. And now you can start to do things in propositional variables, x and y. This goes to, now I'm going to do capitals over here, lowercase over here, x times y. Okay, so here, this is true. If and only if both of these things are true, just like this is equal to 1, if and only if both of these are 1. Okay, you could have not x, so this is the negation, goes to x plus 1. Again, remember, 1 plus 1 is 0 in this setting. And then there's more complicated things you can do. You can do more complicated things like x or y. X or y actually turns into xy plus x plus y. I want to verify this one for you real quick so you can see, so you can believe me. So what we'll do is we're going to check the truth table for x or y. For x or y. So what we'll do is we'll just make like a table here, x, y, and then we'll do this expression xy plus x plus y, and then we'll just kind of plug in everything 0, 1, 1, 1 here. Okay, and then we do this, so this is 0, 0, 0, this is 0 everywhere. Okay, so this is 0 plus 1 plus 0, which is 1. This is good already. We can already see that this is supposed to be x or y, right? And this is supposed to be true when either x is true or y is true, and so it's already worked once. This is symmetric, so we'll see that this is 0 plus 0 plus 1, 1. Okay, here we have 1. 1 times 1 is 1, plus 1, plus 1. Okay, now we're working in this field, F2, right? So 3, remember, 2 is really 0, so this is 1. Okay, so this is congruent to 1. Okay, so this tells us that this procedure that I claimed here is actually true. Okay, so what else do I want to say? I wanted to say that the conversion procedure is general. So I can do any number of variables and convert the propositional sentence here into a polynomial over F2. And then it turns out that satisfiability okay, so there's this thing where I can take a crazy expression and a certain number of variables on this side, like x, y, z, w, however many, and then I can ask if I can find x's values for x's and y's and z's and w's within true or false, so that the logical expression that we have evaluates to true. Okay, and so the satisfiability on this side converts to solving equations, polynomial equations, over this field with two elements. And let me give you an example here of what I mean. So let's look at something that's not satisfiable. Okay, we'll look at something that's not satisfiable, meaning that there's no truth value I can put into it to make it true. And this is the proposition x and not x. So if I'm going to ask that x is true and not x is true, this is never true. If I plug in, both of these things have to be true, but this law of excluded middle prevents us from doing this. So let's convert this. Let's arithmetize. And we see that this becomes, well, from our rules, and is multiplication, and not x is x plus 1, so this becomes this. So this is x squared plus x if we distribute it out. And so the satisfiability problem, so we have that x and not x is true if and only if, well, this equation, x squared plus x is equal to 1, has a solution in this field here. Okay, so this is kind of a weird thing here, but I'm just going to simplify this. This is the same thing. So I just want to say that on this side, x squared plus x plus 1 is equal to 1. This is the same thing as x squared plus x. And so since we're working mod 2, this is the same thing as this. We're equal to 0. Okay, so we can check that this has no solutions. If I plug in 0 here, we get 1 is equal to 0. That's not true. And then if I plug in 1 here, 1 and 1 plus 1 is 0 in this thing. So 1 is not equal to 0. So it doesn't work again. Okay, so this is the equation that we have to solve. Okay, and so this is very similar. This is very similar to the situation where we need to solving. This is similar to solving the equation x squared plus 1 over the real numbers. Okay, so over the real numbers, this isn't something that you can do, but if you make this I, which is the square root of minus 1, this works. Okay, and so you can do something very similar here. And what you can do, so what is the cube root of true? The cube root of true is the solution of this equation. So the cube root of true, well, there's actually two of them, is the solution of this thing, x squared plus x plus 1 is equal to 0. And so what one can do is one can look at this field here, and we can mod out by this relationship, and this is a new field in which we can do propositional logic, where we do new logic. And so in this field there are 4 elements. There's true, false. There's the cube root of true and its conjugate. Okay, so here you can start to develop propositional logic, and then there's a whole field of math here that's devoted to doing this type of thing, and this is called paraconsistent logic. Okay, and so this leads to paraconsistent logic. And so this is kind of a fun thing to do, where you can start to do modify your truth values and to get something kind of fun. So that's all I wanted to say. That you could. So again, what do you do? So what's the whole thing? The whole thing is there's this conversion procedure between propositional logic and polynomials, where satisfiability here turns into solving equations here. Sometimes you can't solve the equations here, but when you can't solve the equations, you just adjoin new things so you can solve them, and then you can continue on like you normally would. Thanks for watching. Bye.